Hi, everyone. It's great to see everybody here. We are extremely excited this week to have Randy O'Reilly with us. Randy's work has personally influenced my own work a lot, but also his work has been very influential in the field for many people, including some folks who have been my advisors at different point in time. So a very fortunate time to be talking to Randy. A reminder, if you're just joining us, and I think probably Jovo's going to introduce Randy because he had the anecdote. So before Jovo introduces Randy, I'm just going to mention a couple of things about the Salon. If it's your first time, welcome. This is an interdisciplinary forum for discussing bridges and contentions between biological and artificial learning. We have participants and guests from philosophy, from neuroscience, from computer science, from AI, from psychology, people working across different species when they come from neuroscience. And it's always a pleasure to get to talk to everyone for a longer period of time. So the presenter would present for 10 minutes, then there would be a discussion. Please ask your questions in the Ask a Question box below and vote on each other's questions. If you have clarification questions, please ask that in the chat area, but keep it to clarification questions so it doesn't distract everyone from what's going on. The chat area is pretty fun, and you should definitely add any relevant papers that you feel like, or feel free to ask a question. There's no question that's not smart enough. If you're a junior person or a person from another field, we do encourage you to still ask your questions, again, in the Ask a Question area. And the highest voted questions, we will invite them to screen, or sometimes some question that we think is very relevant to the flow of the conversation. We try to keep it very free-flowing and with progressive values, so be please kind to each other. Disagreement is okay. Even a little bit of a fun, jokey disagreement is okay, as long as it doesn't border on disrespect. As long as it remains friendly and in good spirit and fun, even strong disagreement is okay. With that, I'm going to hand it over to Jovo to introduce Randy.
Thanks, Ada. So, yeah, I met Randy for the first time when I was about half this age. It's kind of interesting for me, but I was 20. I had no research experience whatsoever, and I decided I wanted to live in Boulder for the summer because all my friends were in a band, and where else would we live? So I emailed Randy because I had just taken a class on his textbook, and I said, "Hey, I just read your textbook. Want to do an internship in your lab?" And amazingly, for no good reason as far as I could tell, he welcomed me into his lab. And it was so kind and generous and unnecessary. And he gave me a little office in the basement, which, you know, I couldn't. That part was a little rough, but I was very happy to be there. And I went to lab meetings and I worked on a project. It was my first modeling project ever. It was on Hippocampus, and it really set me on my research route. After that, I went to grad school to do a PhD in neuroscience and continued doing research on Hippocampus for a little while. That really had a huge impact on my life. So I was always deeply grateful for the opportunity and really grateful that he's here with us now.
Awesome. All right, shall I go ahead and get started?
Please.
Yes, please. We look forward to your slides and your talk.
All right. All good there on the display? Cool.
Yep.
Okay. Well, it's so exciting to be here, and you know, I feel like I'm a little bit of a digital hermit. So getting getting out here and being able to talk with people and everything and really enjoy this discussion is really exciting for me.
So 1 second. So I'm seeing the screen as big as the other videos. I'm not seeing. Do others see it correctly?
Okay. I see it that way too.
Oh, okay. So maybe we need to. So Randy, do you mind unsharing and resharing the slides again? Somehow it's not in full. It's not in full.
Oh, okay. Yeah. Close video. Okay. Then do it. Just start it over again.
Yeah, if you share your screen again, because like we weren't seeing it full screen. We were seeing it as small as a. It's like that again. Oh, no, still not.
I just minimized my face and then it got bigger. Maybe we should all minimize our faces.
Okay.
Oh, now it's good.
We good?
Yeah.
Yeah, go ahead.
Okay, so Yeah, so I'll start off with the big picture. It's kind of crazy that, we seem to know a lot more about learning in lots of other brain areas, but like the neocortex is the most important area for learning. It's the most important area for cognition. And I think we really don't have a consensus understanding of like how the cortex learns. So that's the big puzzle here. And this is my kind of perspective on where we're at here, that we have like stuff that works, basically top-down computational ideas. We have various ideas from the bottom up, but they don't really align, right? So what works is basically backprop. Obviously the huge success of all these kind of deep neural networks, et cetera. But these models, as everybody kind of has talked about, are not particularly biologically plausible in how they propagate error signals backwards through the layers. And also kind of like, where does this magic training signal come from, right? So we don't really have something like that plausibly in ecological terms in biological systems. So there's kind of two problems. How do we do backprop, and where do the error signals come from? And so those are the kind of top-down, the problems with the top-down approach. Here's the bottom-up kind of characterization, which is, this huge amount of understanding about the details of all the kind of processes taking place at the level of the synapse that support, long-term potentiation, long-term depression. And, this basically looks like a kind of Hebbian process, but, there's just one problem from a computational perspective, which is, it doesn't work. These models are not the ones that are solving all these amazing AI problems. And, people can get them to do some things, but they just don't really work anywhere near as well as like a backprop model. So it's kind of an or situation instead of an and. And this has kind of been my mission for a long time in my research, is to try to, integrate these things and get to some sort of synthesis that makes sense of both levels. So there's kind of three different levels you can think about. One is like, how do we do this kind of computational level process? And in particular, where does the error signal come from? And that's a question we can answer sort of at the computational level. And we can understand kind of, the principles of error-driven learning. And then there's this kind of more implementational level of like, well, how does this actually work in the brain? And the kind of new idea here is that there may be particular mechanisms in the thalamocortical loops that can support predictive error-driven learning. And then there's this kind of, question of like, well, okay, does this thing actually work? So I'll just touch on this a little bit. So way back in grad school, I, did some algebra to show that if you kind of rearrange the sum terms in a backprop equation, that you end up kind of being able to compute essentially the gradient of error backpropagation just by looking at differences in time between essentially some kind of minus phase. This term comes from the Boltzmann machine originally, where the network is kind of making a guess as to what the right answer is. And then in the plus phase, it kind of gets the right answer. And the difference in activity state across those 2 points in time actually gives you the error gradient that you would otherwise compute in backprop. So the only thing you really need to take away from this is that delta is equal to basically the plus phase activity of these neurons minus the minus phase. And you can do a bunch of other stuff and show that essentially this contrastive Hebbian learning rule of the product of the sender and the receiver in the plus phase minus the sender and the receiver in the minus phase actually does compute something very much like backpropagation. And this learning rule has been around for a long time. The contrastive Hebbian learning rule was also used in the deterministic form of the Boltzmann machine. So this has a long history. And so this is just basically showing this is how you can do backpropagation without any kind of non-biological processes, taking place at the synaptic level. And this is, there's been a recent kind of resurgence of interest along with all the neural network work and various kind of review papers looking at these different kinds of proposals that people have made. So this kind of contrastive temporal error learning model is the one that kind of I originally developed there with this Generac approach, But there's a bunch of other ideas that people are pursuing, and it's kind of a nice, exciting time to look at these kinds of different ideas for how you might do backprop in a more biologically plausible way. But there's still this fundamental problem of where does the error signal come from? And if you look at people kind of, developmentally, we just sort of have this amazing passive soaking up of knowledge, and then, a miracle occurs and you end up with these kids that can kind of like do all this amazing stuff. How does that happen with so little amount of instruction and so much kind of self-organizing type of learning? And so, one idea that's been very popular, since Helmholtz is this idea of kind of recognition by synthesis, that we make these generative models that we learn by essentially trying to generate the world. And this is kind of consistent with the autoencoder form of learning. Bayesian learning models fit very well with this. And, the seminal work of Rao and Ballard, more recent work by Friston has really emphasized this kind of idea. And then there's a related, but actually slightly different idea, which unfortunately uses the same word prediction, but uses it in the sense that, this famous kind of quote emphasizes, which is about predicting the future, not just kind of generating the current input, but rather predicting what is going to happen next. And this is actually an idea that Jeff Ellman and his colleagues has pursued a lot in the 90s. In the first kind of wave of these kind of neural network models, and showed that you can kind of learn a lot of important structure of language, for example, by learning to predict what's going to happen next. And Word2Vec and a lot of other current, BERT type models are using these same approaches, really, that go back to the pioneering work of Ellman. And so that's kind of I think there's a pretty solid consensus, as far as I can tell, that predictive learning is really going to be important for understanding how ecological learning works. And I would say, I don't know too many people who would disagree with that statement. So that's awesome. We have some idea, but there's still this question of how it would work biologically. And here we've been pursuing this idea that the thalamocortical loops, as identified by this really important work by Sherman and Guillory, have the ingredients to do predictive error-driven learning, especially in this kind of about the future sense of the word. And the key idea here is that you have top-down projections from the deep layers of higher levels of the visual cortex, synapsing on these higher order thalamic neurons, for example, in the pulvinar of the thalamus. And those provide a great opportunity to sort of like generate a prediction. And then this really remarkable pathway, these feed-forward driver projections come in from these cells that are known as the intrinsic bursting cells of layer 5. These are actually the same type of cells that are the primary motor output cells in frontal cortex. But they have this really important property that they only fire kind of roughly every 100 milliseconds. And they provide a really strong kind of driving force onto these cells. And so when we looked at this, we thought, that looks like a training signal. That looks like something that's teaching something. And then this looks like it could be the thing that's being taught. And that gives you the ingredients for a kind of error-driven learning mechanism. And so this is the idea that essentially you're kind of coming up with predictions, these images, so to speak, of what you think is going to happen next. And then that feed forward kind of driving input from the intrinsic bursting cells periodically, every 100 milliseconds gives you that plus phase kind of training signal that says, here's what actually happened. And so here's our kind of diagram of how it happens over time. We can kind of go into more detail on this if we have further questions. This is our latest attempt to try to explain this, and I think it's quite difficult to kind of put together all the issues of layers and time, et cetera. But the key idea is that, over this period of this 100 millisecond kind of bursting cycle driven by these layer 5 intrinsic bursting cells, you first kind of get some kind of like prior context from what happened last. You use that context to generate a prediction on these kind of pulvinar neurons that is essentially what you think is going to happen. And then while you're generating that prediction, there's no bottom-up input coming in from the lower layers to sort of like contradict that. So you just kind of have the opportunity to create the prediction. And then at this moment, kind of, when these layer 5 intrinsic bursting cells from the lower layers like V1 here burst, they give you the right answer. And that difference in time between kind of the activity state across the pulvinar is the error signal. And this is really important and kind of hard to understand in a lot of ways, that the error signal is not explicitly computed as like, the neural firing of a particular population of neurons, but it essentially remains as a temporal difference, this implicit difference over time between essentially this kind of plus phase versus the minus phase. And so that obviously nicely fits in with the previous kind of theory of how error-driven learning works. And because the pulvinar is sending these projections back up to the rest of the cortex, so it really does sort of function a bit like a projection screen. And we can talk about the Cartesian theater for those who might be interested in the kind of philosophical implications of this. But it is kind of a little bit of a Cartesian theater here, where these signals are getting broadcast back up into the cortex. And so there is this sense in which like your entire cortex is sort of staring at this projection screen of the pulvinar. And because that error signal, we think, is being broadcast up so broadly, then all these different areas that are generating and contributing to the prediction get to benefit by sort of learning on that temporal difference. So they can locally compute their error signal and actually compute a local, very biologically plausible synaptic change equation that reflects this global kind of objective function of improving your ability to predict what's going to happen next. Okay, so that's the key idea. And I think, the question of like, does it work? We found that it actually produced, pretty interesting categorical kind of representations in a large scale model that was kind of looking at various objects kind of floating by and saccading around looking at these objects. And it seemed to categorize these objects according to different shapes that made sense. And the representations that formed in our model look a lot like what you see in macaque areas, where like the V4 area in the model is kind of sort of categorical, which you can see by these kind of block diagonal kind of blue things. But that when you get up into the higher levels of the network, you really get this kind of really solid kind of categorical type of representation. So the model does seem to be producing some kind of categorical learning in higher levels along the lines of what you see in the visual cortex. And we can quantify this and see that, in fact, as you get higher up into the visual hierarchy in this very kind of large scale complicated model, it does actually seem to be forming kind of interesting abstractions based strictly on prediction error. And this is kind of the bottom line point here, is that the only thing that this model is learning on is predicting what essentially the next frame in the video is going to look like. And strictly through that kind of, predictive process of the raw sensory input, it is able to develop some kind of interesting abstractions higher up. And that is one of the key questions about, the whole idea that predictive learning can be a useful solution to this big, question of where do the error signals come from? It's only useful if those error signals are somehow able to drive useful abstraction. And otherwise, it's just kind of like sort of memorizing what's going to happen next, but it's not really creating a useful internal model that has these kind of higher level abstractions that we know kind of exist in the human brain. So this is some, kind of very preliminary evidence that maybe this kind of predictive learning actually might do that. And it turned out that kind of the bidirectional connectivity of this network, similar to what we see in the cortex, the inhibitory competition, some amount of actual remaining Hebbian learning that's mixed in with this error-driven learning, those things also seem to be important when we compared it with other kind of purely backprop type of predictive models. And so there's still a lot of work to be done to understand kind of maybe some biases in the learning process that enable it to produce these kind of more categorical representations. Okay, so I'll stop there and with my 10 minutes, so to speak, and we can go to the questions.
Thank you. So you definitely had more time. So if it's okay, I'm going to play a little bit the role of just unfolding some of the slides,
okay.
Hopefully a little bit. If you have more slides that you wanted to show us, please feel free to show them also.
Well, I could just show you, we did run an experiment and basically tried to see what do people do when they see these same shapes. And here's the kind of similarity, representational similarity analysis of what you see in people relative to what you see in the model. And this is, a little bit hard to evaluate exactly, but the overall similarity structure does seem to fit pretty well with what we see in the model. And I think when you look at these kinds of categories and sort of blur your eyes, certainly with the vertical versus the horizontal, these seem like pretty clear categories. The box as well. The pyramid, some of these ones look pretty reasonable. Some of them are a little bit random, and that actually turns out to be true in the model too. That it isn't. There's some exception cases in here that don't really quite line up. But yeah, so basically, it does seem like people do sort of, when presented with essentially the kind of fairly low resolution view of the world that our model is seeing, and without any other kind of semantic information available that of course people have, people do seem to use the same kinds of categories. So there may be something reasonable about that. Yeah, so summary, basically, here's the optimistic take here is that maybe this provides a getting to the and here, a synthesis that actually connects the top-down kind of computational principles of error-driven learning with these kind of actual biological mechanisms that might actually work. And of course, there's a lot of work to try to test out whether or not these specific ideas actually apply. And we're doing a lot of interesting further modeling work looking at kind of applications to motor prediction, like a forward model, cross-modal predictions. And there's so much work in the field these days looking at things like successor representations, et cetera. And these kinds of predictive mechanisms, I think, are really, being explored at a lot of different levels. So it's an exciting time to be working on these kinds of models. Okay, well, that's fine. I think that's good. It accounts for these predictive remapping effects that are these classic, this is basically, showing that the brain does generate these predictions kind of at this 100 millisecond time scale. That's the last one. All right.
Yeah, thank you so much.
Thank you.
So I'm just going to ask like a clarification, just in case it might help myself and others. If you go to the slide that you had with the Emergent model.
Yep.
Also, is this in Emergent, or is there like a Python-based new version that you're using?
There is a new version. Yes, there is a new version that the underlying kind of computational guts are in Go, and you can run everything in Go, which is this new language from Google. But then there's a nice Python wrapper around that as usual, so that you can access everything and program the models in Python.
Awesome. Is there a name for the Emergent Go version?
Yeah, we just called it Emergent again.
So I'm seeing it on GitHub. I'm gonna copy the link and let me know if this is the right link for the audience to just take a look.
Yeah, yep, that's it.
For those who don't know, Emergent was the software where the figure on the right that you see on the slide was used for doing neural network modeling for cognitive scientists, not for CS folks. So this was a cognitive science specialized way of modeling the hippocampus, entorhinal cortex. People like Anna Shapiro have used this, like even they still use it up to today. And this was a standalone software, so it's very good to have like a version of it that's on Python. Because I remember that in 2013 it crashed my laptop. So here I just wanted to ask you. So what I really like about this, and I immediately thought, oh, this is really like the work that I do for representation learning. I love the fact that you're using a simple temporal difference learning principle that has nothing to do with rewards. It just has to do with
Yes.
exactly. And I really appreciated that. So what I wanted to ask is whether there is a different temporal difference signal that is being used at all the different layers, and that's how you get the abstraction.
Yeah, and so that's a really important point, that each of these layers is has, you know, essentially we're now kind of introducing the kind of laminar structure of the cortex in addition to kind of these area levels. So we can talk in terms of like areas like V2, and then lamina like superficial versus kind of deep here. And so the superficial layers in each area are all talking to each other directly through these kind of bidirectional connections. And those are the kind of connections that we had previously in our existing models, that, you know, simulated error-driven learning, and where we thought about all these kind of error gradients propagating. And so that is still happening. And that's this kind of like little arrow here that basically says, in addition to this kind of pulvinar broadcasting of prediction error up into the cortex, each layer is also directly computing its kind of back-propagated error signals, essentially, from higher layers coming back down through this kind of classic, you know, hierarchy of visual areas, you know, from TE to TEO to V4, going backwards down here to V2. And so that back propagation of essentially these error signals from higher layers to lower layers, and likewise the feed forward propagation of information through those same pathways, is really important for shaping that abstraction. So you've got kind of like the classic notion of a hierarchical kind of visual network there, where higher levels are able to form these more abstract kind of categorical representations. And then kind of superimposed on that, this sort of like broadcast of error signals, but essentially each layer is interpreting, if you will, that kind of error signal kind of in its own language. It kind of aligns with it, with the specific representations that are forming in each of these layers in different ways. And so that kind of local temporal difference signal is going to be different for every layer, just like you said.
One thing that I really liked in what you said is that there is some recurrence happening because of the two-way relationship between some layers, right? And something that I wonder now about this is, so some folks really like convolutional neural networks for mapping the visual cortex hierarchy. However, as we know, CNNs are very bad at adversarial examples, which are things that don't throw off humans at all. We see the same panda, but because of the noise added, all of a sudden it's categorized as a gibbon. That was the Goodfellow in 2016. And then in 2018 or 17, there was this other paper with adversarial patch. So there is a banana on the screen, and there's the CNN categorizes it as a banana, but you add a patch just next to it.
Yeah.
And all of a sudden it says it's a toaster. So there are many sort of examples like that. I wonder whether you have tried adversarial examples, and it seems to me like your approach might be more robust to those.
Yeah, I think it would be. We certainly sell it as such, you know, for our funding pitch. But you know, and I think the top down, bottom up attractor dynamics, like you're saying, are exactly kind of a key element there. That, you know, it's trying to make sense of what it's seeing at the higher level, and that comes back down and is kind of, you know, trying to essentially resonate with this like attractor top down, bottom up kind of classic Hopfield network level kind of dynamics, to create a consistent interpretation. And we do think that is going to be really important for reducing the adversarial kind of, you know, sensitivity to these little tiny perturbations. Another thing, you know, I have a lot to say about that, but another kind of key point is that the existing models are not really solving the visual recognition problem in the way that the human visual system does, because they're kind of integrating across the entire visual field in parallel, and they end up essentially learning object recognition as essentially texture recognition. And there's a lot of evidence in these models to support that idea. And so they're kind of not picking up, like we think about like shape as like the most important, determiner of like what an object is. But these existing models are really looking at essentially the sort of overall texture of the patterns across the image. And I think that's where a lot of this adversarial problems come from. And there's this really nice paper that came out of Poggio's lab a few years ago, where they actually took one of these models and just had it sort of essentially saccade with kind of visual attention on different parts of the image, instead of trying to do object recognition on the whole thing kind of holistically. And when you do that, they got rid of a huge amount of the adversarial kind of problems. And this model that we have here also has that same characteristic, that we do have essentially a dorsal pathway up here that is in fact focusing top-down attention through just the same kind of top-down connections from this LIP parietal area that has these kind of hotspots for different spatial locations. That's coming down and kind of focusing attention on different parts of the visual scene. And so we think that aspect that, again, that was in this Poggio model is also going to be really important for adversarial robustness.
Absolutely. I've actually linked the Poggio paper here before, but I will add it here after this. Cool. I think it's fantastic that you have extended, and it's not just about saccades, but actually attention.
Yeah. So I think both of those. Yep. Both of those are really important. Again, this kind of thing about like, what can we learn from the biology that might improve these AI models? And I think those are two definitely good examples.
That's really awesome. I really like this. Another thing, and maybe one last thing, again, just clarification about this model before we move on to questions from the other two hosts on the screen. I just wanted to ask, what is the capacity or computational capacity of the model? So how many, basically, let's say for 10 items or 10 categories, how much, I guess, how big a model does one need? Like, how does the model scale? Is it like
Yeah, so that's a really important question, because the number of objects that we presented here was 20, and there were roughly 10 or more instances of each of these different categories. I'm showing you kind of like one instance of each of 20 different categories, but we did have, essentially 10 times that. So roughly 200, it wasn't quite 200, I think, actual like, specific 3D models that we showed. And then the network was shown these things kind of just rendering in all sorts of different kind of little movies. And one of the things to emphasize also with these models, because we're predicting the future, you need to have a meaningful element of time in training this model. And so you need to have essentially videos, not static images. And so that's a really important constraint on the learning that we think, obviously is true about the real world. People don't just learn on static images, but it does make it so that you can't just sort of like take ImageNet off the shelf and run the model on ImageNet and expect it to do something interesting. But the other thing that's going on here is that you have a 100 millisecond kind of, top-down, bottom-up constraint satisfaction settling process for each individual image within those videos. And what that entails is also, the need to have, top-down connections. So you've got twice the number of connections, roughly speaking. You've got 100 times the number of essentially compute cycles per image. And then you've got, the fact that you're training on videos and not isolated images. So there's, we had very, very short videos of only 8 frames, but still that's a factor of 8. And so when you basically put all that together, you you have something that takes forever to train. And so we found, even with this really tiny V1 kind of representation, this is a 16 by 16 kind of spatial size of V1. Each little kind of box down here in this bottom end of the model is different oriented kind of Gabor filters. We didn't have it learn those first level Gabor filters. We just kind of pasted those in from what we knew worked pretty well. So it's a really intensive model computationally. And so we haven't been able to scale it up very much. This takes, over a day to train when we split it up on 32 processors on a cluster. It also hasn't been really easy to get it running on a GPU in an efficient way, because there's a lot of sparsity in the activity and in the connectivity. That's something that is not very easily translated onto GPUs efficiently. And so we've tried various things, but we haven't really gotten very, high level of advantage on GPUs yet. And so, so the bottom line is it really hasn't been tested from a scaling perspective.
Thank you for that. And is there any plans of adding any kind of a memory module so they can be at least compressed somewhere after a category is learned and only activated if it's needed?
I mean, I guess you mean just like episodic memory kind of thing, or what? I'm not really sure what you mean by that.
More like maybe semantic memory. So there's so at any given point in time. So I'm not sure how, because of exactly the computational capacity that you mentioned, it makes sense that at some point in my day, I don't need to have, for instance, a dinosaur memory activated, but my brain is perfectly capable of categorizing dinosaurs if I ever see an image, right? It would make sense that I have consolidated some compressed representation of the weights for the dinosaur category somewhere, and it's not always there, so that my currently active on task kind of visual network is not bombarded with everything, right? So that's all I wanted. Whether there is
you could definitely kind of take these high level representations which have that kind of visual aspect of the world kind of in a high level form, and then have that be part of a semantic network that feeds on top of that, for sure. That would be easy.
Thank you so much for answering all of these. I'm very excited about this. I could ask a lot more, but I'm gonna leave it to John and Jovo.
Great.
John, shall I ask questions next?
You're muted, John.
What did you say, Jovo?
I said, I'll ask my question.
Go ahead, yes.
Okay. Randy, I'm just going to close your slide so we can see each other better. So that was cool. It reminded me of being
the basement,
in your lab 20 years ago, where you, it was always so impressive because you would just come up with this idea and be like, here's how I think the brain works. And you're just like, do some modeling thing and be like, yeah, that seems right, approximately. So that's impressive. But I guess, so I have two questions for you. One is, there's obviously been lots of models somewhat like this over the last, 20 years, whatever. Can you just, I think I got a little bit lost in the weeds. Can you explain again, just like what's the one core thing that you feel like you've changed about the previous models that gives your model these new capabilities that are able to match the human properties?
Well, there's two parts to that. So I think one part is basically like, the key thing that's different about the model relative to existing models per se is, essentially this idea about how the corticothalamic circuitry could support this kind of predictive learning. And as far as I know, nobody's sort of come up with a similar idea at that level of like, where is a prediction represented, and where is like the error signal relative to that prediction kind of computed, and how would that all play out in the brain? When you look at existing models, again, from like Friston, Rao and Ballard, going back to that tradition. Those models all kind of hypothesize a population of neurons in essentially the superficial layers of the cortex, layer 2, 3, that explicitly encode like prediction error. And so these are neurons that, basically, if you experience a difference between what you predict and what you see, they fire literally like in proportion to that error, to that difference. And one of the kind of, particularly surprising things about those models when you kind of work through that idea is that they actually say that if you correctly predict what you're going to see, there's no firing in like, your cortex. And so, sometimes it feels like that. But on the other hand, I definitely, there's been a lot of papers written kind of, looking at that question and saying, well, it isn't quite like that. And there's various ways of getting around that issue, different ways of thinking about how the kind of prediction error coding coexists with other kinds of activity signals. But, it's not something where, like, despite a lot of ideas out there in the literature, that, like, it's clear that that's how the brain works. I think there's a lot of controversy about the idea that cortex is explicitly coding for kind of prediction errors. And so this provides a pretty different alternative here by keeping the prediction error as that temporal difference. So if I was to say, like, the most important difference in this proposal relative to these existing ones is that we retain this kind of temporal difference form of the prediction error, and that kind of allows the system to be constantly representing essentially a positive representation of the world. You're always representing kind of what you think is happening at a kind of, again, this kind of notion of like a positive representation, what you think is there, okay? And either that's a prediction of what you think is there, again, in this kind of minus phase time frame when you're essentially predicting kind of what you think you're going to see. And then that's, replaced in time with this kind of right answer of like, oh yeah, that's what I actually saw. And so this idea that you're kind of always representing kind of the positive thing, as opposed to taking the difference between, this sort of top-down prediction and your bottom-up, kind of reality, and representing that difference literally. I just think that proposal has a lot of issues that I don't see aligning with, like, you stick an electrode in the brain of a monkey and the neurons are sort of like always coding what the monkey is seeing. You don't see them kind of representing like nothing when expected and boring stuff happens. They're just like always seem to be encoding kind of like what the monkey is seeing. And so it just seems like a more quote unquote natural way to represent error as a temporal difference, because then you don't have to have like all these conundrums that come about when you try to represent error kind of like explicitly. So I think, that's the biggest kind of, kind of more maybe neuroscience level issue about like how we might think about, predictive error learning. And then the other side of it, to your question is like, what is it about the model that allows it to predict human data and generate these abstractions? And that, has a lot to do with like the detailed structure of the layers in the model and how they're connected, and the kind of the fact that we have a separate pathway for doing the kind of spatial prediction error. And one of the things we discovered with this model was that by having a kind of separate kind of where pathway in the dorsal stream, that essentially factorizes out the spatial prediction error, and it leaves the kind of object prediction error, the feature kind of prediction error, as a residual. And it turned out that in the way that the model learns, it first learns to do the spatial thing, which is kind of easier, lower dimensional. And then again, yeah, it has that residuals, the residual error in a kind of regression type of terminology, goes up and is essentially slowly absorbed by the ventral pathway, the what pathway. And that kind of division of labor between those two components of prediction turned out to be really important. So that's, I think, one, kind of more detailed aspect of this specific model, beyond the broader kind of principles of how prediction learning might work, that allows it to actually kind of like produce those abstract representations that seem to align with what people are doing.
Can you say a bit more about the factorization of where and what? Because that's something that, as we all know in the Salon in the past weeks, it's kind of argued for what happens in the lateral and medial internal cortex and the hippocampus, kind of like figuring out what's where, and the association where in medial internal cortex supposedly the graph lives or the structure. Lateral internal cortex gives them the object, and hippocampus has the binding. So it would be awesome to hear your perspective from before these areas.
Yeah, exactly. Yeah. So, and I think it's interesting, how much the recent attention is focused on entorhinal, and things like that. But I do think that those principles obviously, go all the way back to these, classic kind of what versus where division in the visual cortex. So I think, that's really the source of all that. The MTL type guys are reflecting that division, but it originates way back in the earliest levels of the visual stream, in terms of this kind of dorsal ventral route. And the idea that your kind of dorsal stream represents essentially, an abstract encoding of things like space. And if you go to higher levels, presumably spatial relationships, right? Something is above something else, something's, next to it, something's larger than something, these kind of more quote unquote relational abstract representations. I think the idea that is akin to essentially a kind of syntactic representation, an abstract schema-like representation, and that's really essential for how we kind of encode like episodic memory. These are actually ideas that my colleague here, Charan Ranganath, has pursued for a long time. And one of the major motivations for me to move to Davis here was because we really see eye to eye on that, and have now been collaborating on models that kind of take up that idea. So I think that really fits in with this kind of a lot of work that people are doing in this general area on that topic. But I guess my one little kind of point here would be, you could look earlier in the visual system and see all this stuff happening, and like a lot of people are just so focused on entorhinal cortex and are sort of and the grid cells, and that becomes such a kind of like a tractor of thought that people have. But really, all this stuff kind of is coming from these more basic earlier visual stream representations, and in some sense those earlier ones are the source of all this stuff, and you're just seeing sort of higher level abstractions and integrations, and kind of more episodic kind of processing of those divisions as you go up into the medial temporal lobe. Yep.
Cool. So, and then I have one other question, and it's kind of a meta question, and related to the Salon more generally. We've had people that approach trying to understand learning from, your perspective, obviously. We've had other people like Gary Marcus talk about very different approaches, or people talk about meaning, other people talking about kind of fundamentals of statistical learning, or the deep learning engineering. And all of these are approaches that different communities are now basically research approaches that we're taking. We're all kind of have similar goals. And I wonder if you could just talk for a moment, like this approach that you're using, what are its limitations? Like, what will you not be able to explain about learning? And where you think you'll fail? Like, who do you think, or what field do you think will kind of come to the rescue, if anything?
Yeah, that's a great question. I think the kind of scaling questions that you were just talking about, like when you get into a more kind of detailed biological type of explanation, that obviously is going to entail a lot more computation, a lot more detail, And so that's something where having more abstract levels of models can allow you to sort of capture, the higher level cognitive functional type of principles, and and scale up to take advantage of the power of big data, as we're seeing in these big deep neural network kind of models. Those principles are things that we're not going to be able to capture anytime soon. I wish we had better kind of hardware to be able to try to scale it up, but even then you could easily make the argument that you just get buried in the details anyway, and you want to have these more abstract frameworks. And so I'm always looking for ways in which people working at these different levels of analysis have compatible abstract higher level ways of thinking about things that I can learn from, that sort of okay, yeah, here's a principle for how the structure versus content type of distinction, going back to Fodor and Polishyn, right? I think those kinds of arguments have a lot of power, and can be stated very succinctly and tell us very clearly, this is how the system should work. And so, I think there's, especially, given my perspective on the field, and I trained with Jay McClelland at Carnegie Mellon University in my PhD. He was always kind of, somewhat, really relished these debates, and loved to, kind of engage in these somewhat, kind of controversial discussions with Pinker and Prince, and all this kind of stuff about neural networks versus symbolic models, and Gary Marcus obviously being someone who comes out of the Pinker tradition, et cetera. And so I think there has been this kind of sense of historically these opposing perspectives on things, but I think when we start thinking about what's happening in the dorsal pathway and the MEC and these kind of structured representations that are going on there, that's exactly what Pinker and Fodor and Polishyn, et cetera, have been talking about. And in fact, Polishyn literally has this idea about fingers of instantiation, which is his kind of terminology for understanding what's happening in the LIP. It's basically this kind of notion of essentially an abstract pointer-like representation that can say here's this thing and here's this other thing, and what's the relationship between those two things. And I don't care what the detailed features are of those two things. I just care kind of what their spatial relationship is, for example. And so that ability to abstract away all the details and just capture the kind of structural relationships is, critical for having generativity, the ability to take existing knowledge and apply it to brand new situations in really flexible ways, and so if you look at all the work that people are doing on analogical reasoning, it's exactly that kind of thing. You take a kind of deep representation of the kind of structure of a situation, like orbiting, right? This notion of orbiting. That's this kind of very abstract, spatial kind of relational structure. And now I can take that kind of concept and apply it to all different kinds of phenomena because I've formed that kind of very abstract representation. And so, those kinds of ideas are ideas that can be explored at all these different levels. And probably this biological level is not the most productive way to say, yeah, this is powerful, because it's you'll just get mired in all those details, right? And so I totally am a big fan of kind of multi-level modeling, and more seeing the connections, as opposed to battling out as this is the only way to represent something, or to think about things.
Cool. Okay, thanks. That was helpful.
On that note, I want to ask one more thing, if that's okay, a follow-up, which is, you have this one. So I've been collaborating with Anirudh Goyal and Benjio, and they have done some very nice work in this area. So I guess a twofold question. You have this wonderful workshop paper, the deep learning needs a prefrontal cortex. And since I started my journey into cognitive neuroscience from the prefrontal cortex, that was a very dear to my heart paper, and I recommended it to everyone. I wonder in where you see, so we already saw that you have the attention and the LIP parts, which might be actually key and central for the top-down predictions and attention that might get us out of this kind of constant situation with adversarial examples. But I wonder, where do you see the role of prefrontal cortex, both in terms of the directing of the attention or goal-directed imagery or analogical reasoning, because we know that there is a role for especially Brodmann area 10 in the prefrontal cortex that seems to be very special in humans, especially the medial parts of it. So I wonder what you think about generally the role of prefrontal cortex in this last part that you mentioned, that you went from abstraction to relational reasoning and analogical reasoning. What do you think about the role of prefrontal cortex in that and in your model, as we know your models have always had an eye on this?
Yes, exactly. So first of all, I want to give a shout out to Jake Russin, who's the lead author on that paper, and he's a grad student in my lab, and he's amazing. And he gets full credit for that paper. But it does build on sort of ideas that we have been developing over the years about prefrontal cortex. And I think the kind of ideas that we've worked with previously in frontal cortex is essentially that how much can you explain about what it does just based on the idea that it can kind of maintain information in an active state over time with these kind of latched kind of gated attractors, and we've connected that down to like the connections with the basal ganglia, interestingly also going through the thalamus. And one of the interesting things that I feel like I'm learning over the years is just like how much does the thalamus do in connection with the cortex in kind of controlling and gating and modulating and regulating and training, what's going on in cortex. A lot of that all goes through the thalamus. But anyway, so that idea that, prefrontal cortex can kind of hold on to something and then provide a kind of top-down bias, like an attentional signal, a top-down task signal kind of thing. That is essentially the kind of classic idea. It goes back to work that John Cohen has done, Earl Miller, all these kind of classic ideas in the literature. And so, yeah, I totally agree with all those things. I think one of the most exciting things more recently is, in neuroimaging, you always see PFC in it, coactive with parietal. Okay, it's just like they're almost inseparable. And so what is the connection between, the parietal, what parietal's doing and what the PFC is doing? And I think here, one idea that comes out of this predictive learning framework is that the parietal is essentially sort of taking a potential action that the PFC might be planning, and telling you essentially this kind of model-based prediction of here's what would happen in the world if you took that action, right? And so if you think about a kind of action-based, goal-directed kind of framework for thinking about what the brain is doing overall, which of course we think is very much what the brain is all about, is like we're always trying to achieve some kind of overall outcome or goal, and we're always thinking about active ways of taking the next step in our cognitive or physical actions. And then you need to sort of essentially represent, oh, well, if I did that, here's what would actually happen. And then that's where the predictive learning comes in, because it basically tells you, yeah, this is what would happen if you take that action. And then you can use that in reverse to essentially say, well, here's the action that you want to take to achieve the outcome that you actually want to achieve. And so if you have parietal essentially representing the outcome that you desire, and that's activating frontal representations to sort of choose the right action to produce that outcome, that gives you a much more kind of interesting, I think, synergistic relationship between the parietal and the frontal. And that's kind of the current thing that we're trying to really understand in our models, is like how, these abstract, structured, kind of relational parietal representations that also tell you kind of like here's what would happen if you take this action in these kind of abstract schema-like representations, how that integrates with like, planning and thinking about what next step you want to take cognitively. So I think if we can figure that out, we'll be pretty excited. So yeah.
For what it's worth, every single fMRI work I've done has had PFC in it, but not all of them had co-activation with parietal.
Okay.
But I don't use just GLMs. Other people, I use multivariate analysis, but people who use GLMs alone also observe, for instance, in, I think, analogical reasoning papers that folks did at Berkeley and then at UBC, just comparing the analogical reasoning versus a comparable case. So to take out everything else and just keep the analogical reasoning.
Yeah.
It turned out there are many situations where it's not co-activated with parietal, but I totally understand what you're saying. It is puzzling in many cases when they are co-activated together.
Yep.
We also know that if the PFC gets damaged and the parietal is intact, you still see impairments in behavior.
Mm-hmm.
So it's interesting to see, for instance, if Brahman area 10 gets damaged, but nothing else gets damaged, people can't do hierarchical planning.
Right.
And it was beautiful work from Paul Burgess in the early 90s. So it's interesting that the kind of to see where are the situations where parietal plays a role that is necessary for a task or is really linked with PFC, and when can it not compensate for PFC? I think that these are very cool questions.
So I'm curious though, so I definitely agree that like if you didn't have an intact area 10, like this idea that you couldn't kind of like juggle multiple working memory states and do that kind of outer branching, stuff that Sylvia Bunga talks about, that kind of idea makes sense to me. But then I guess I'm curious, like I'm not really on top of this literature, like is there anything looking at people with damage to parietal that does show any evidence of like, planning like deficits if you did have just a parietal lesion?
That's a very good question. So what I know about parietal lesion work was about imagery, because there was the whole thing of the hippocampus versus parietal. So it turns out mental rotation parietal can handle mental rotation even for people without a hippocampus, but other kinds of imagery, if the hippocampus is not there, it can't. And with BA10, so what I was referring to is at the front by the Paul Borges group, it was they gave a series of tasks to the person and they said, go and buy a paper from this shop, a pen from that shop, and then write a letter and post it at the post office.
Daily activities kind of thing.
Exactly.
Yeah.
And then normal people will go like this.
And
the BA10 damaged people would just zigzag and not finish the task.
Right.
Which was very interesting.
Yeah.
I don't know of people who focused on the parietal in that work, but I definitely know of people who focus on the parietal in prospective memory literature, which is very related.
Okay. Yeah.
But as far as I
some
know,
causal role maybe there. I don't know.
I haven't seen that, but it might have been that it was just maybe people were looking for prefrontal more. I don't know. So I have to look again for the causal role that you're mentioning. I think that's an interesting thing to look at.
Yeah, because that's such a challenge with neuroimaging, obviously, with all the kind of collateral damage, collateral effects. Its co-activation could be totally, epiphenomenal. And so like, really trying to see like what actually matters is so important.
So we do, however, that temporal parietal junction, if it even gets zapped by TMS, people's theory of mind gets messed up, which is another kind of branching.
Right.
So we know that some kinds of specialized branching, at least, and also numbers. So especially right posterior parietal processes magnitude, and if that gets zapped, I will get bad at judging magnitude. So we know those things. So there is something that it does. But I'm not sure if it's in task coordination as much as those other aspects. But sorry, this went too long. John, I'm sorry. I'm going to be quiet now and let John ask his question.
Muted.
Too late. It's too late because while you're all talking, I've been drinking whiskey, so now I have nothing. So Randy, I've been a fan for a long time, and I've read a lot of your stuff. listened to chunks of your courses. And, you know, I've been listening to you, and I kind of like the project, if I understood it, which is you have, I think you're on record of saying, look, isn't this architecture interesting between thalamus and cortex? And it's got a kind of logic to it that made me think about predictive learning. And that's not that different from people who stared at cerebellar circuitry and basal ganglia circuitry. And there was a logic from the learning standpoint. And in a sense, you started by saying, we've got cerebellar learning theories, we've got basal ganglia learning theories, and you've now come up with a cortical version. And it's a similar kind of way that you did it, which is you got quite granular. You looked at the actual circuitry, right? Which is good. I would actually like to say to you, and I won't dump all my concerns and questions you at once because you won't remember them. But it seems to me that when it comes to learning and the brain, the granularity of the circuitry, whether it's in the basal ganglia, the cerebellum, or the cortex, seems to be the right level with which to get an idea about what the learning rule is. Would you agree that when it comes to learning, I'll talk about performance in a moment, this is the entry point, a sort of look at the circuitry, think about the substrate, and then algorithmize the learning rule from that. Would you say that's a fair description?
Absolutely, yeah. And I think it's really interesting, especially in contrast to like this recent paper with, you know, a lot of co-authors, Richards being the first, and kind of making this point about, you know, neuroscience has it all wrong. We're kind of, you know, spending too much time looking at the details of neural circuitry and neural activity, and, you know, we should be thinking about objective functions. And so that's kind of the complementary idea that, you know, you want to think about what is the goal of learning, formulate that as a kind of loss function, and derive the learning rule, and don't worry about all the details, right? And so this kind of more classical, you know, approach, which I associate, you know, originally with like Marr, you know, his seminal papers in 1969 and 71, were just kind of like, just like you're saying, stare at the circuitry, look at what that suggests, and come up with an algorithm that, you know, kind of like fits with those details of the circuit. And especially when you look at the cerebellum, I mean, it's such a exquisite, you know, differentiated circuit that, you know, it's so compelling that something is happening with all those kind of crazy pathways and cells that are so specialized. And so, you know, I think the idea that, you know, cortex is amenable to that same kind of approach is perhaps more controversial because it is, you know, a lot more, it's not as distinctive, right? I mean, you don't have like a Purkinje cell in the cortex that just screams out to you and says, you know, this has to be doing something important because it's so weird. There's a lot of, yeah.
But nevertheless,
yes, I did.
You did something like that, right?
So yeah, so it may be
right.
You know, I could see that's certainly what I found it obviously to be kind of inspirational to puzzle over that circuitry and try to think about like what could this be doing. And I think there the equivalent of the Purkinje cell is these layer 5 intrinsic bursting cells, and they're very striking projections onto the thalamus. And those projections are, you know, kind of like the climbing fibers in the cerebellum. They're very kind of, they're described as glomeruli, and they're very kind of massive and highly specialized. And so it does have that same kind of like, there's something important. Evolution is doing something here. And so you should pay attention. It's like a little flashing light that says, you know, this circuit is not just like a generic thing. It's doing something very important. So I do think that there is that kind of, you know, kind of highlight there that does kind of, you know, if you don't have an explanation for what those things are doing, then, you know, maybe you're missing something.
Right. So I like the contrast you draw between getting real clues from implementational level details to have a sense of what might be going on in terms of the learning rule. And I do think it's interesting when you look at the sort of Blake Richards coding paper, or even the Lily Crappen coding paper, where they sort of say, well, where they agree with you is that it's much easier, whether you do it top down, like they're kind of saying, or the way you did it, that you can say something compressible about the learning.
Right.
You can say, right, so learning seems to be amenable for you to go error-based,
right,
associative learning,
right,
reward-based learning, predictive error learning. There seems to be
right,
something about learning, regardless of whether you do it MAR level 3 or MAR level 1, you can at
right.
least agree that you can say something in a talk, right?
Yeah. Yep.
Now, so that's great. The problem I have is when you mentioned Alan Newell, and I'm an Alan Newell fan, and I admire the sort of almost functional computational approach that he took to common
Right.
sense and thinking, where he actually, as you know better than I, but he talks a lot about cordoning off levels, and he talks about the difference between physical laws, neural laws, and representational laws, and says that as you get to cognition, which is what his target was,
Yeah.
you can become less and less implementational in your concerns.
Right.
Right. And so my concern, if I can call it that, with your talk is that it seems to me, and I want to get your genuine opinion on this, that if you want to look at asymptotic performance of a cognitive task, not how you learned to get there,
Right.
then the implementational stuff isn't anywhere near as easy to talk about than the learning rules themselves.
Yeah.
So I get the feeling that we can be implementational and have fun at the level of neuron details for learning.
Yeah.
But it doesn't seem to give anywhere near the satisfaction when it comes to actual thinking. And there was an evidence for that in the way you were talking. I'll quote you during your talk. You said, what you think is going to happen.
Yeah.
Right? So in other words, you use that very abstract word, what you think is going to happen versus what does happen, and then you do some sort of subtraction.
Yep.
But what if you want to know what thinking itself is?
Yeah.
Right? Rather than just doing the subtraction on that thing that you kind of take off stage. You give it, and you also said something like in your slides, I'm trying to think, prior, the prior was doing a lot of thick work, right? What did the last thriller that I watch? Who was the baddie? Right. And so you guess that the baddie in the Agatha Christie is going to be the one with the most English accent. Of course. But so in other words, what I feel you've done is you live in this newer world, or have given up on it, which is more functional, computational, cognitive, and gone and done learning where you can get all neural on us.
Yep.
But I defy you that you're going to be able to be equally neural when it comes to the actual content of thought. Do you see what I'm saying?
Yeah.
Can you explain to me how you live with this contradiction?
Well, I think that goes back to, it's, obviously excellent point there. And to me, it goes back to this issue of, multi-level modeling and that you can't do everything at one level, right? But on the other hand, if you have, what you're looking for is continuity, and so we see this, in all the sciences, right? So you don't do genetics using quantum physics, right? You just don't, right? There's a level of abstraction at GCTA and the genome that gives you a very clean separation between levels, but the actual behavior of those molecules depends on quantum physics, and how they bind and how they shape the proteins and all that stuff. And there are aspects, that do depend on that, right? And this kind of protein folding question that people are looking at is a very complicated emergent phenomenon that isn't perhaps so easily kind of separatable. But I think throughout science, you always have these different levels of analysis, and you have to be able to kind of work at different levels in order to be able to understand the right phenomena at the right level.
Yeah, we've talked a
Yeah.
lot about this at the Salon, and of
Yeah.
course,
Yeah.
I mean, when you put it in that sort of
Yeah.
deeply diplomatic way, one can't disagree with you. What I'm saying though.
You want some
is,
more controversy, don't you? I need to get my
it's
whiskey
not that
going here.
I don't want controversy. I'm not at all. But I think that what I'm asking is, you know, you make a lot about if you want to understand something, you have to build it.
Yeah.
Now you
Yeah.
can't you can't really mean that, because that means that, you know, astrophysicists and particle physicists don't understand anything because they can't build elementary particles, which would be
Right.
absurd, right? So,
well,
what you really mean is what you really mean is, I think what you mean, if I've understood you correctly in your previous talks, is it's very useful to be able to simulate something.
yes. Yes.
Right.
Yeah.
And I think that's extremely interesting about your whole project, if I understand it, which is, isn't it fascinating that you can simulate computationally all sorts of cognitive phenomena?
Absolutely.
And it's actually very interesting when you look at people like, you know, Piccinini and, you know, Milkowski that we've had on here, you know, that cognition seems to be something you can simulate.
Yeah.
Right. You can rise above the implementational details.
Yeah. Yep.
And then you say, yes, that's true, but maybe the implementational details will provide some constraints on our simulations. Something like
right.
that.
Yeah. Yeah.
Right.
Absolutely.
Right. Okay.
And yeah. And, you
Go
know,
ahead.
an issue with a lot of simulations is like, okay, how much are you putting in as assumptions versus kind of what the model is telling you, kind of like beyond what you already built in, right? And this is always this question, like when somebody makes a model, especially, you know, I think you mentioned Newell, you know, some of these more symbolic kind of models, a lot of times it's kind of like, okay, you made a model with everything really explicitly kind of set out, and the model did basically what you thought it would do because it's, you know, it's was designed to do that, right? And so that question of like emergence, right? What emerges out of the model that isn't something that you kind of like just basically forced it to do in the first place? To me, that's where the, you know, interest is, and that's why we call our software emergent, and kind of really also why learning is such a magic process, right? Because learning is, you know, that kind of thing where you really get something for nothing, right? And one of the things that you can see in like all the symbolic models is that, you know, they're kind of starting out with existing representations and showing how, like, if you assume a set of existing representations, so take, for example, these models of analogy, right? They build in the representation of like this abstract understanding of like orbiting, and they build in the fact that you can kind of like map that onto, with like symbol binding kind of power, swap in new kind of like variables into, you know, the binding relationship. And like, yeah, of course that works, right? And you know, at some level of description, it's important to know that it does work. But on the other hand, it's like, what have we learned by doing that model?
Yeah. So
And
you've made this.
especially, yeah, especially I just
You've
want to
made this
add,
point.
yeah, I want to add one thing, which is like people have now made neural models that essentially implement those symbolic models. And in particular, there's a whole line of work where people have taken these tensor product kind of models, for example, and shown that if you have a tensor product kind of neural network framework, it can do essentially symbol binding and, you know, propositional representations and everything, just like you could when you did it in, you know, Lisp. And so, you know, there's a question, right, of like, okay, is that model kind of at the neural level telling us something interesting or not, right? And there, I think, like, to me, the thing I really want to get to that does connect back to the biology, I think, is like, how the hell does the thing actually learn, you know, kind of like from the ground up at some level to form these abstractions and to be able to reason and think, the big think term.
Yeah, but this we keep
yeah
but we keep coming to that, right? I mean,
yeah
but knowing how you learn to get to something
yeah
isn't necessarily going to tell you how you do it once you've learned it.
No, I
right?
disagree. I just go. So here I'm gonna take some bait and have some controversy and not be so diplomatic. That I think that the abstraction of having a clean propositional. I always get the wrong propositional. Yes, kind of symbol binding framework is too simplistic for how the brain actually works. And that, yes, at some level of abstraction, that's kind of capturing something obviously important about how it works. But here, I would say the way that a learned neural representation actually does sort of this symbol-like structured schema, structure sensitive, whatever term you want to use, kind of reasoning process is not going to be isomorphic with the existing symbolic models, because the existing symbolic models require mechanisms that don't exist at the level of the brain, and that there's something also about how, we have a metacognitive level of ability to understand what we know, and we can manipulate the internal representations, and how and the internal representations are kind of distributed patterns of activity. At the same time, they're amenable to some sort of metacognitive understanding, and that kind of thing, that we have essentially an explicit knowledge representation that is made of neurons, and that is also kind of like bidirectionally connected and kind of subject to constraint satisfaction, and kind of like all these dynamics that we think are really important. To me, that's like the huge question. That's the unsolved mystery of cognition, is like, how does that work? And I don't think that existing symbolic models are capturing kind of the magic of that. Nor do I think that existing deep neural network models are capturing the magic of that. I don't know exactly how to capture the magic of that, but my gut feeling is that it's not something that kind of jumps levels so easily and is transparent across levels, that it is sort of an emergent phenomenon of these brain systems, and that, probably we need to understand a little bit more about the biology to solve that problem.
Yeah, I mean, I just to finish, you see, the thing is, when you say what you just said, and referring to Paul Smolensky, who's trying very much to sort of find a way to live between sort of implementational
yes.
and the symbolic, which I am very sympathetic with. I think he's absolutely right that you have to find some way to align those, right? And, from the philosophical side, Carl Craver's talked about that. But when you say, well, there's got to be some more biological detail that we've yet to unearth that is going to be very important to sort of ground how we think about that symbolic stuff. That might well be true, but there's nothing in what I've heard from you that actually makes your case any more strongly than thinking that it may be more neural-like. So am I fair to say that there's nothing that you've demonstrated that makes that case? Is that right?
Yeah, you got me. Yep.
Right. Okay. No. Okay. All right. That's it. That's great. So there are lots of people who want to talk, I'm sure. But thank you. I love the whole project. Just so you know.
All right.
Don't get me wrong. All right.
Cool.
So Randy, I think that there was, while you were talking, there was I think a clarification question with some of the more junior members of the Salon, and it would be very helpful if we kind of get it maybe on screen so that it's not an individual conversations. So I think that there is, perhaps I'm going to scroll up to find the relevant ones. So there were two questions that were relevant here. I think one person was asking, okay, so Atta was asking, okay, someone posted something and I lost the location. So first, the question was about prediction errors and the temporal difference predictions versus the top-down and bottom-up hierarchical predictions. So I think a lot of people, unfortunately, have only heard of reward prediction errors.
Yes.
So I think the first question that someone was asking was, is this similar to reward or value prediction errors? And I was explaining to them that prediction error is a more broad term. One kind is related to reward, but there are so many other kinds. For instance, sensory prediction errors or space prediction errors or successor prediction errors. So that's one part of the kind of clarification. The other part was a question they asked about a paper that you did mention, and they were asking, first of all, how related is your idea of temporal difference learning and top-down, bottom-up difference in prediction versus experience with the notion of prediction errors? And second, how is it related to the paper by Rao and Dana Ballard on predictive coding in visual hierarchies?
Okay, so starting with the reward prediction, the key. So it is a very similar concept. So in reward prediction, you're basically taking, cues that exist and trying to predict, like what is the future reward that's going to happen, at the value of something in the future based on those cues. And so there's the widely known kind of TD model, the temporal differences model of reward prediction error, RPE, reward prediction error. And so mathematically, it's extremely closely connected. The idea that, you're essentially taking something at t-1 and using that to predict an outcome at t, so that temporal difference is critical, that you're actually predicting the future. And you're learning on the difference between kind of what happened and what you predicted. And so at that level, mathematically, it's extremely closely connected. The difference, of course, is that in the way that people think about TD, it's associated with dopamine, and that temporal difference error is explicitly coded by the firing of dopamine neurons. And this is extremely well supported, in the brain, that, neurons in the ventral tegmental area that release dopamine, their firing kind of is modulated directly as a function of, did the reward that I expected actually occur or not? If it didn't occur, if I expected it and it didn't occur, I get a reduction in that tonic firing rate. If I didn't expect a reward and I got a reward, I get an increase in that firing rate. And so that is an example of a explicit error coding representation. And the temporal difference is about kind of you're using information from the prior time step to predict what happens at the next time step. But the error signal itself is not coded as a temporal difference itself. And this is really confusing, right? So it's the TD algorithm, but the TD about it is kind of in the nature of like what information you're using to predict relative to the outcome that you're predicting. But the error signal is explicit in that sense. And this then ties back to the Rao and Ballard approach, where again, they also use explicit errors. Okay, so they have this idea that there are neurons in the brain that literally, as a result of top-down connections coming from higher levels and bottom-up connections from lower levels, that there are neurons that literally compute the difference between those two pathways, right? So the top-down is the prediction, the bottom-up is the kind of reality, and a neuron in the middle is, through a combination of excitatory and inhibitory connections, literally computing the difference and coding that similar to a dopamine neuron as a difference in the firing of those of the neurons, explicitly encoding the error signal. And so so again, in our framework, we're thinking that the error signal remains as a temporal difference. Again, not in the sense of the dopamine signal, but literally as like you have a state of activity in the network, and then you have a new state of activity, and the error is essentially implicit in the difference in time, that temporal difference in time between those two states of activity in the network. So that's an attempt to
have both the top-down versus bottom-up and the temporal difference?
Yes. And exactly. So at each point in time, you always have all parts of the network kind of communicating top down, bottom up. And if we go back to the kind of mathematics of how you might do error backpropagation in the brain, this 1996 paper, it was really important that all layers in the network are kind of communicating with each other in both the minus phase and in the plus phase. And this is a very subtle point that I think a lot of people don't get in thinking about like how backprop might work in the brain. One idea, again, this kind of Raoul Ballard, et cetera, idea is that the top down tells you a prediction and the bottom up tells you the right answer, okay? In our view of how the cortex is working, in the superficial layers, that's not the dynamic, okay? The idea is, in fact, that both layers are collaborating in both phases of the processing. And so in the minus phase, the top down and the bottom up are working together synergistically to come up with a prediction. So it's not like the top down is the prediction and the bottom up is the right answer in the superficial layer of the cortex. Rather, they're kind of collaborating together at that level. And so that's a really important distinction. And I think a lot of people find it very intuitive to think about like that top down versus bottom up difference kind of, literally all top down connections are predictions and all bottom up connections are kind of ground truth. We do think that's happening in the thalamus, but not in the cortex. So it's like, it's a little bit complicated when you start kind of thinking through those different ways of thinking about the circuitry. But that's a really important distinction, and those are really good questions. So yeah, I don't know if that helped clarify it or not. But
so by top down and bottom up right now, did you have in mind layers of the neocortex, or did you mean, for instance, prefrontal
areas,
visual cortex? Right. Exactly.
Yeah. So layers just within like layer 1, layer 3, 2, 3 versus 5, 6, or those lamina. I like to use the word lamina because that doesn't get used ambiguously for different areas. So yeah. Yep.
Awesome, thank you. So we usually invite on screen in order the top voted questions. And first we have Laureline, and please go ahead. Hi, Laureline, good to see you.
Hi, so thanks for inviting me. I'm a postdoc at the CRE Center. I work on the effect of thalamus and basal ganglia on cortical dynamics with applications to hierarchical motor control and robust artificial networks for out-of-distribution generalization. So topics that are related, but more on the motor side. My question is a little linked to actually what John asked. Because when we're talking about prediction, I'm thinking most often about cerebellum. Cerebellum is thought to compute this type of prediction that would take into account both the world and the effect of our actions on the world. So this may look a little different a priori, but given that passive perception is very rare, if not absent, you kind of always need to have both together. And so I'm wondering a little bit, do you expect that those are really two separate computations that are being done in the brain, more motor related in cerebellum, just sensory related in sensory area and thalamus? If so, why? Do you think that there's really something specific about the structure of these sensory circuits? Or do you think that it's more something about developmental constraints or other types of constraints in the brain? As it's always a little hard to know whether when we observe something, this is like something functional or, a constraint.
Yeah. So I think that the cerebellum is in particular doing the same thing. So it's clearly, that's the dominant model, that it's a sort of forward model, a predictive model, but that it is specialized for very fast timescales, right? And so this idea that some people have advanced that, the granule cell population in the cerebellum forms a kind of rapidly changing, drifting temporal code. So you get some sensory signal coming in there, and then these granule cells kind of unfold very much like a reservoir computing kind of idea at the more abstract kind of neural network level, that you get this kind of rich distributed, encoding of time. And then, the Purkinje cells can basically learn, like, at this moment in time, something, important is going to happen, and I should probably fix it, and usually what happens at that point in time is an error, something unexpected, right? And this is the kind of classic Albus Marr type of model of the cerebellum. And then, you want to be able to essentially anticipate that error and, correct it in an anticipatory fashion, so that next time around you don't make the same mistake, right? And so the idea that the cerebellum is, essentially this predictive learning system that anticipates errors and then corrects them, I think makes perfect sense. But the time scale of what you can do in cerebellum relative to cortex is much different. So in cerebellum, it's like really like 10 millisecond kind of precision. It's very fast. These patterns are drifting very quickly. Whereas in our cortical, predictive framework, we're, especially when you think about the critical role of those intrinsic bursting cells, they go at the alpha frequency, every 10 hertz, 100 millisecond time scale. And so that's going to be a predictive learning essentially at an outer loop, longer time scale that's more kind of like cognitively relevant or perceptually relevant. And so with that system, you're not going to be able to like really correct like an in-flight ballistic arm movement, which is unfolding very quickly, because the timescales are just wrong. So it is kind of like the same motif, the same idea, the same overall principle of learning, but implemented in these two different circuits, and obviously like the cerebellum got there first, evolutionarily, and it's very important that we have like these motor pathways learn effectively, and so that's kind of something that happened, but it happens at this time, at this finer time scale. So that's interesting. And also one really interesting point that just to follow up there is that the cerebellum projects back up to the cortex via the thalamus. So it is a driver onto the primary motor cortex thalamic area. So like area VL in the thalamus, ventrolateral thalamus, its primary driver pathway that is akin to like the training signal that we're hypothesizing in our predictive model, that is actually coming from the cerebellum. Okay, so the deep cerebellar nuclei project up to there. And one of the classic things that we know about the cerebellum is if you have cerebellar damage early in life, it's very impairing. But if you have cerebellar damage later in life, it actually doesn't have that much impact. So it does seem like the cerebellum is a learning organ, right? It's something that helps the system learn. But once it's kind of helped you learn, then you don't depend on it as much for kind of like online processing. And so that actually could be the cerebellum providing a training signal into the thalamus of the motor cortex, basically of this same type that we're talking about for the kind of predictive error-driven learning in sensory cortex. In motor cortex, the cerebellum could be the source of like the ground truth signals, essentially passing on that predictive error signal up to the cortex saying, hey, you should fix your motor program because it's going to go wrong in a second, in a millisecond. Yeah, so I think there's a pretty interesting potential like whole like story about the relationship between the two.
Thanks. Yeah, that's very helpful.
Cool.
Just before Melanie comes on and before Lauren leaves, I mean, there's so many things there that I actually disagree with. It's not the time to go into. No, it's really it's actually it's just. I mean, I just, for Laurelyn's sake, because Randy, you're too far gone. I think prediction is a very slippery term, right? I think when it comes to the cerebellar forward model story, the idea there is that it actually literally simulates what might happen, right? And the current story is that that's probably true for control, but it's very difficult to show that that's actually what's being used for learning. Okay, so that's one thing. I think that.
So what if it learns to predict errors instead of learn to predict? What if it's not a model like a simulation, like you're saying, but it's actually learning, again, this distinction of like, are you representing the world or are you representing an error?
Right. I think the idea that it might be responsible for the generation of a sensory prediction error that then feeds into another learning mechanism, I'm much more sympathetic with than it's running a simulation, which you then
and that's a key. Okay. So that's a key distinction.
Right.
Yeah. So what it's predicting may be different, but it's doing some kind of prediction. Yeah.
And then in terms of what the cortex is doing, the notion of anticipation, right, I think is quite different from the notion of simulation.
Yep.
Right. So I think we also have to be very careful about that. Right. So I just think that the idea that they're doing the same thing in the cortex and cerebellum is just a question of the time horizon. I don't think that's too.
Yeah, no, there's a difference in the signal. Yeah.
Yes. So I think that's very important.
I think that's reasonable. Yeah, I don't know enough to really know like the details of all that, but that I have a sort of vague feeling like, there may be some difference in what the cerebellum is actually coding relative to what the cortex is coding.
Right.
Yeah.
So maybe just to jump on that, if I understand well, or if I, it looks like what makes it difficult to kind of like pinpoint in the cerebellum is if this is some error that's linked to the learning of some circuit, then it's just hard for us to map it to something when we record. Like, what is the nature of this explicit in a general setting? Of course, most of the cerebellar tasks are like designed to be such that the error is extremely explicit, right? You have this signal that's on the screen such that you really make it. So then you have like those beautiful results from Reza Shamer. But I guess it's maybe the nature of what it's trying to predict on top of like the time scale is what you're saying, right?
Yeah. I think for sure the time scale is, that's an easy kind of differentiator, but it sounds like this difference of like what is actually being predicted is another differentiator. And again, I actually had a postdoc who worked with me, who had a specific idea about this kind of, it's coding the error, it's predicting the error, as opposed to predicting the positive state. So I have just a little bit of a sense of that idea might work. But so I guess one question, is how far away are we from like being able to actually do like a kind of, decoding level analysis of what the signals are in the cerebellum to really get at this question of like, what the heck is it actually coding? Like, has anybody done that, or is that work underway, or is there any sense of like figuring out what these mysterious cerebellar signals are actually about?
I don't know from John's side, but there are certainly some people, including me, that are interested in trying to use unsupervised algorithm to see whether we find some sort of like clustering of the signals in more complex tasks that are not necessarily easily like visible relative to the signal itself, but that may still have some sort of relationship to the task that's just more complicated than what we see in, say, simple saccades task, right? Or, but there's no...
Nothing definitive quite yet about that? Okay.
We'll see if I get to do it.
That'd be exciting.
Is there a cognitive, because I remember some people claim that there is some cognition-related things that happen on the cerebellum, but as far as I understand, it's so fast that it might be more related to timing and motor, fine-grained motor sort of control, but also in timing because of certain sort of smoothness of timing, for instance. Is there something actually more cognitive than timing and motor control?
Yeah, so, and there's the cerebellar cognitive syndrome has quite a lot of stuff that goes beyond timing. You're absolutely right, Ida. I think the really interesting thing about the constellation of cognitive deficits from, psychomotor processing speed and other verbal deficits is what the whole field is wrestling with is whether you should take the forward model idea that's worked for the motor system and try and bend it to come up with a cognitive story for it, which I'm not sympathetic about, or whether there's something more fundamental about the cerebellar architecture, which for the motor system works as a forward model, but it's used in some other way for cognition, and that we should consider forward model its motor adaptation, but it has another adaptation for cognition, rather than to try and couch all of it in terms of forward model. That's the kind of feeling I get. So the story, what Randy was saying about the projections via thalamus to prefrontal cortex, it's obviously playing some kind of tugboat-like function for cognition, like it is for others. But I don't think we know what that is yet. I think we have to be a little bit more. It's a little bit like, I think, Randy, just for something you've said, which I think would be the audience would very much like to hear, is when you say a structure has a macro function versus a micro function, right? You've made that point before, right? Where a system makes a unique contribution to a behavior versus it has a kind of enhancement function on the main area. Is that right? When you say so, and I think you think hippocampus is a macro structure, obviously cortex is a macro structure, but I think that you feel like the basal ganglia and maybe the cerebellum are more like microstructures. And Laura Lynn's done some very interesting work as well, where she shows that to enable cortical function, the subcortical structures sort of soup it up, right? So does that fit that these subcortical structures are micro, including the cerebellum, or do you think?
Yeah, I mean, macros? I guess so. Just to my specific use of that terminology, I think, is more along the lines of just like the architectural level, and it's basically what you said, but just to clarify a little bit, just like the macro structure is kind of like specialized information processing systems that are working together again at this kind of macroscopic level. So there is this like ACT-R framework that has modules, and it's like the modules of cognition. So this idea that the hippocampus is a declarative memory system, and that's what it's doing, and the prefrontal cortex is this control system, and that's kind of the macro level description. And then the micro level is like, how does the actual circuitry in those areas kind of support these different kind of cognitive functions? What kind of specializations are there, like the ability to maintain active memory states over time in prefrontal cortex? That's a microstructure level issue. And then, in that context, like basal ganglia doesn't, as far as I can see, have an ability to influence cognition or motor behavior that much outside of ocular motor directly. It like does everything kind of in its influence over the cortex. And so it's like, at that level, it's not like a separate module, because it's like so interdependent on the cortex that you can't really understand what it's doing kind of like independent of the cortex.
Right. And what about the cerebellum in that context? What would you say about the cerebellum?
Right. So, I mean, clearly it has this kind of teaching role to the cortex. I don't know, like, what happens if you have a decerebrate system that still has a cerebellum, what kind of functionality that has. I don't.
Zero.
Yeah.
If you're a human, you're dead, right?
So it sounds, but like in a rat or something, you're like, can it still walk around? I mean, is there sufficient spinal and deep projections of the pontine, output nucleus or whatever?
I can tell you the answer to that. If you remove basically all of the hemispheres in a rodent, you can get remarkably intact behavior in a way that you would never see in a primate. You'd be anencephalic. It's fascinating. But anyway, it's a fascinating talk.
Sorry, so I just want to, so just one thing clear, just like with words, not like, it doesn't need to be like sentences, whoever knows on screen. So other than smooth motor control and timing, what cognitive effects does cerebellum have that cannot be explained by these two already, by timing and motor? So I haven't heard anyone mention anything else, right? for hippocampus, we can name what the functions. For frontal cortex, for parietal, we're not sure entirely of all the functions, but we can name some of them, right? With cerebellum, I know of the motor smoothness and timing, but everything that people mentioned, it seems like it might be explainable with timing. So I don't want generic things like ADD or things like, yes, but what is the principle? Like someone is mentioning that there is a relationship with ADD. I'm not sure what's the relationship between that and cerebellum, but anyway, so does it have to do with timing only, or is there something you can, some kind of a cognitive function you can mention, just words?
Yeah, I mean, I'm by far an expert on this, but they have problems that go beyond that. They have problems with grammar. They have personality changes. They have other affective changes. They can be inappropriate in social situations. So it goes beyond just a sort of general slowing or a timing problem. It's actually more than that. It's a psychiatric as well as a neurological.
But is it quantitative in its effects, or is it qualitative? You know, those are tricky distinctions, but like there's a sense of like you don't have a hippocampus, you don't have episodic memory. Like it's a really big difference, right? Whereas my sense is with cerebellum that it's like impairing some of these things, but you still function, but you're just not as good, right? And so that's I think
I mean, I think
like
honestly,
booster.
Schmarman and others have all talked about this, and you're right that you could probably at the current time, and maybe other people who are more interested in this, to both of your points, is that can you be ataxic in many areas, right? And it's absolutely true, to be ataxic in all these other things is not the same as lacking it altogether, right? If you have an ataxic reaching movement, you're still reaching, right? Yes, I there has been this back and forth. Is it a qualitative lack, or is it just a clunky version of everything that you do, right?
Melanie, can you come back? Like Melanie just left. She says that she can't ask her question. Oh no, we lost Melanie because of the cerebellum.
The other thing I've heard is sequences. Like John kind of mentioned grammar, but I think timing, sequences, timing, grammar, motor control are all special cases of sequences.
I agree, but not large scale, right? It's again within a certain sort of finer grain sequencing. And also everything that John mentioned, if I think about models like the one that Randy has, and we just mess up with the cycles of the neural network, you can get a lot of different kinds of effects, but it's not because the region that was messing up with the sequences or cycles is controlling those or is important in those cognitive functions.
I think that's correct. I think that's correct, Ida. I think that my take is that it's modulating what other cortical areas are doing and messing it up a bit, but it's not doing like what the hippocampus does, is you lose that memory. I think that's correct, actually, but I'm not enough of a person in that area to say that, but that's the impression I get, is it's modulating. Yeah.
But yeah, John, I think, sorry, I'm definitely not an expert, but it's not that it's messing it up. It's like kind of providing stability to sequences.
I mean, based on what do you mean that? Based on what study?
The same like the tremors or like your time, like things get
out of time. So that's the game about timing.
Yeah, sequences.
And also that's just one other topic that's very dear to my heart and other people that we've worked with, is that one mustn't confuse sort of sequences with sequential continuous actions. They're actually quite different. One's quite cognitive and the other one's motor, and they tend to get conflated. And there's no question that continuous sequential actions are interrupted by cerebellar damage. When you get to sequences in terms of discrete elements, it's a much more difficult situation. But we're going way off topic. I feel bad. I think Melanie.
Yeah, Melanie, I'm so sorry that we missed Melanie.
Why did she go? Because she.
Jovo, can you invite Paul Chisek, please? Because they had a question. I hope he's still here. It's getting late, so we have to be careful that we don't lose. Next time with Melanie, we should first ask her how long she has.
We lost Paul. We lost Melanie.
Oh no. Okay, we're gonna read Melanie's question because it's John's typewriter is back. It's making it. So Randy,
know,
John's typewriter is a recurrent guest on the Salon. It's very loud. John claims it's from the 30s. We don't know
The
if this.
gaming keyboard.
I don't know. Honest, I think it's his laptop. It's just that his sequence generates very loud sequence. Cerebellum generates very loud sequences.
you see, do you see, Randy? You see what I have to put up with?
It's tough. It's a tough crew here.
It's all from love. It all comes from love. Okay, so maybe we can read Melanie's question. Melanie asks, there's a spectrum of possible details that could be in a prediction error signal, ranging from prediction is wrong, but no additional details, to here is all the details in how prediction is wrong. Where do you think those cortical error signals fall in the spectrum, and does it depend on context?
Yeah, that's a really interesting question. So, if we talk about this idea of like the dopamine prediction error, that's like at this extreme end of like a scalar prediction error, right? So it's like a single kind of like value, and it's just like, were you off or not in that single scalar outcome? And then, this is very much a vector error kind of prediction thing, in the sense that in our little picture there, the pulvinar is like representing like an image of what you're predicting. It's a detailed rendering, so to speak, of like what you're expecting to happen. But what's also really interesting is that the cells in the pulvinar that have been recorded from, and also in the deep layers of the cortex, have much broader tuning curves compared to those in the superficial layers. And so we actually can kind of use the neuroscience to answer that question a little bit, and say that, in fact, we're probably making vaguer predictions than what we're seeing. And computationally, that actually is likely to be quite useful, in the sense that it's probably pretty hard in general to exactly predict what's going to happen next. But if you can kind of make a reasonably kind of like approximate prediction at this kind of vaguer, more broadly tuned level of representation, then you're more likely to be able to get that right. And then you kind of don't have all these like nitpicky error signals, but you have like the big picture error signals, which are the ones that you need for like, training the system, at an appropriate level. And so that's a kind of interesting computational level kind of question. Like, you could just say, in any kind of predictive learning system, does it work better to use like a blurred kind of outcome representation as opposed to a very precise outcome representation? Does that allow the system to kind of, do better overall? That does seem to be what's happening in according to the data. Yeah, but anyway, it's much more on the detailed level. And then another really important aspect of that question that comes up all the time is like, what is the time scale of the prediction, right? And so in this framework, we're talking about like low-level perceptual areas, V1, V2, V4, making predictions every 100 milliseconds. And so this is predictions that are sort of below conscious awareness. They're so fast, if you really kind of listen to something that's happening at 10 hertz, it's really quick, right? And so you're not like, these are not the kind of predictions that you're thinking, oh, I thought when I opened this door, when I pulled the door handle, the door would open. It didn't open. That's a much longer time scale of like prediction error compared to what we're talking about with these very fast time scales. And so there's going to be predictions at the level of like frontal cortical actions that, I tried to do this action and I thought I was going to succeed and that didn't work. That kind of much longer timescale prediction is sort of perhaps a different mechanism yet, in addition to what we're talking about with this kind of posterior cortical thing. And that's a further question of like, what are the circuits that support that kind of prediction error? And these are the things that give rise to like the P300 and the error-related negativity and, all this stuff that people talk about, at this kind of like 300 millisecond to 500 millisecond kind of ERP signature of like error-related processing and stuff. So yeah, so there's a whole another time scale there that needs to be dealt with.
I'm very glad you said that, because it ties in very beautifully to the question that Paul Chisek asked, who is also not here, sadly left early, had to leave earlier. Paul asks, would you suggest a similar scheme for learning beyond the visual system, including different sensory modalities, as well as learning in non-sensory regions of the neocortex?
Right. Yeah. So I think it fits really well with other sensory modalities. John Rorlick is someone in my lab who's working on this exact model applied to speech, and there it's actually a much better fit than in vision, because speech obviously is such a temporally richly structured kind of signal, and so there's a lot to predict and a lot to learn. And ultimately, there our goal is to get a model that closes that loop with motor production and sort of learns how to produce speech by predicting, what would happen if I made this motor action, and these kind of classic ideas that have been developed. Frank Gunther, is that it? BU has a model like that, and so that kind of sensory motor level kind of stuff I think works. It works for motor control at a finer time scale, and again, perhaps in collaboration with the cerebellum at some level. And then this question of this longer time scale is like a bigger question that we need to probably prefrontal cortex and basal ganglia and maybe dopamine. Maybe that's really what's happening at that level, and who knows, maybe anterior cingulate cortex is doing something. There's a lot of players there that we need to understand better.
So to answer Paul's question, you think that even in higher order neocortical region, this kind of predictive contrastive learning could be a decent sort of learning mechanism. And I agree with you actually on that. So we have another John K on screen, just to confuse everyone. Hi, John, welcome.
Hi, can you hear me? Good, I was getting echo a second ago. Quick question. So your frontal parietal model seems like trying out actions. Are there, is this always overt action, or there could be covert actions which would allow for deliberative processing, test out a few and select one? And that seems different than cerebellum, where I don't know that this covert action model would apply.
Yeah, definitely. Yeah, we think a lot about that kind of covert action idea, especially kind of the idea that you're using these circuits for planning, exactly like you're saying, so that if you have a model in your mind, a predictive model somewhere. I mean, this is a classic idea about what the virtue of having a predictive model is in the first place, is that it allows you to run simulations, right? Mental simulations. And so, yeah, that you could have a planning process that essentially involves, well, what if I did this? Oh, what if I do that? Okay, well, that looks better. So that kind of internal perspective planning process, I think, is definitely one of the key things that you would use this for.
To me, and so that fits sort of with conscious deliberation. Does it expand to that time scale pretty comfortably?
Yeah, and there I think it's like the parietal level, like we're talking about, kind of prediction of the outcome, sensory outcome of an action. This notion of parietal as sort of perception for action kind of idea, that makes sense of a component of that. So it's basically the model part of it. So it's essentially you generate a perspective action in frontal cortex, you see the potential sensory outcome of that in parietal lobe, and then you iterate. But that iteration, that deliberative iteration, is exactly that kind of cognitive level, outer loop kind of processing, where you're essentially saying, oh, what about this? What about that? That whole kind of time scale is built up from multiple of these kind of like faster inner loop steps, of which this core kind of very fast alpha time scale predictive component is like the inner loop of that. So I think that's the way I think about it, is essentially there's a deliberative outer loop that's kind of using this inner predictive kind of mechanism as a component of it, but it's more this systems level phenomenon that then makes sense of it being conscious, if you think about consciousness as kind of interconnecting all these different areas, all focused on a common problem. that's kind of what you're seeing at that more deliberative level.
I would just one thing to that, you know, if I have a little bit of cognitive dissonance about that notion, because if you're going to be able to deliberate over the potential consequences that the parietal cortex generates, why couldn't you have just deliberated over that yourself in cortex? In other words, if you can deliberate, then deliberate the whole thing. Do you see what I'm saying? It doesn't quite fit for me.
Huh. Well, I mean, one idea is that it takes multiple areas kind of representing different aspects of things. So like, for example, the parietal would encode like the spatial and relational and kind of event schema like outcomes, okay? The implications for like in a social relationship, you know, talk about this theory of mind kind of stuff or whatever. But maybe, you know, infratemporal cortex is going to represent like, you know, the actual like, you know, object content information that would come as a result of an action. And whenever you need to have multiple areas collaborating and coordinating, that's, you can't just sort of like do it up front. You need to take basically the time to get all those areas to talk together. And you can't kind of like short circuit that, because each one is contributing some subset of the whole problem, and they need to talk to each other to do that. And that's basically what consciousness is taking all the different specialized representations and getting them all to work together to solve a problem.
So in other words, just so I understand, so the other night we couldn't decide whether to watch Minari or Nomadland, right? And we were going, should we watch this or that? Are you saying that I need relational parietal cortex to decide what? I mean, I just, rather than just saying, well, Minari's this story about a farm and a Korean family and Nomadland. I mean, but it just seems like it's shoehorning something into something that doesn't quite compute to me.
I don't know, tautologically, like if you could make the decision quickly, you would have. So in other words, there are decisions you make quickly, right? You just do it, right? And then those are the ones that you didn't need to have all that deliberation, back and forth, conscious, you know, reverberation, whatever.
Surely you're not going to say that whenever you're deliberating over something that you don't decide immediately, it means that multiple areas are talking to each other.
Yeah, I do agree with that. No,
but we don't have any evidence for that, right?
Let me jump in and a little bit of evidence. You only can consciously think of one thing at a time. That suggests to me that if you were able to do modular stuff, you could process all these alternatives in parallel. I don't think that happens, at least by introspection. And I suspect it does take a lot of cortex interaction to get to this level.
Yeah, and so we have a recent paper, Seth Hurd in my lab has been a real advocate of this idea for a long time. And so he has a paper that just came out that kind of makes that case that in fact exactly that we do a lot of decision making through a sequential deliberative process, and that's why we do it, is because it does require that coordination. So yeah, and it's like the global workspace theory, exactly that kind of idea that a lot of people have about consciousness is exactly the kind of idea that builds on.
One last thing, I know it's getting late, but one last question that I have been meaning to ask for an hour now. So relationships like is next to, is on top of, or so those kinds of sort of relational representations. Transformers seem to be good at learning those. And they have like attention heads, and there's some weights there. And because of the weights, they can learn in different contexts, for instance, this or that. There is some work that we're hoping to do in analyzing what kind of relations these sort of learned representations have. And for instance, something like successor representation could be a special case where transformer is learning to navigate. But then when it's learning to figure out, is my laptop on top of this book or is it next to the book? Then it might be learning something else. And it would be interesting to see whether there is a more generalized version of learning that is happening there. Is there something or some intuition, do you think, from the way that these attention heads learn these kinds of relational representations that would be adapted into your kind of tradition of emergent models?
Yes. So actually, Jay McClelland has a recent paper in PNAS that is kind of trying to make this case that, in fact, the transformer architecture is capturing what, classically in the early PDP models we talked about when we said constraint satisfaction, that it's basically focusing attention on a particular possible interpretation and playing out the kind of possible connections of that, and that a transformer can do all of that in parallel. Whereas, again, we were saying that we think in the brain that probably does require a more sequential process. And so one way, just generically, to think about a lot of what's happening with those kinds of models is they're essentially, again, in parallel, sort of like in dedicated, replicated neural hardware, doing what we otherwise do in the brain with this kind of sequential, iterative, bidirectional kind of communication across neural layers. And so that's my kind of like generic understanding of that. And it is, there's always been this kind of question of like, why do we have the neural architecture that we have? And could we, with some crazy AI singularity thing, just, scale that up in some massive way and make it work so much better? And when you look at these transformers, it really does have that kind of characteristic of sort of taking this process that we do sequentially and just kind of literally like replicating it across all this hardware. It is kind of, that kind of idea, I think. But what it loses is, I think, this kind of workspace plenary kind of notion that we have about a kind of continuity and coordination of thought over time. And so it's a little bit like maybe too parallel. And again, I don't know enough about like how the different heads on the transformers like coordinate at the end, or where they coordinate, or maybe there's some issues there that might be really interesting to explore. But anyway, that's a lot of vague thoughts about potential connections between like this kind of bidirectional processing across layers in the brain versus what's happening in these transformers.
Thanks. Did you mean the paper he had where he was
Yes. Yeah.
So actually, he was at the Salon last semester, and he presented it. That's I really like that paper.
Yeah.
Yeah, I was making another kind of comment, because there is a kind of a relational representation that humans learn very easily, like is to, like that structure, and then I can apply it to anything.
Yep.
You can apply it to the plant is next to the window, or the lamp is next to the sofa, or the book is next to the laptop, right? So that is something that transformers do learn, but to the extent that I know that our neuroscience neural networks are not very good at that.
Yeah.
That's
do transformers learn them in that kind of abstract way, in the sense that they can actually apply it sort of generically? Is that true?
So the version of the recurrent independent mechanisms, it's a version from Anirudh Goyal and Yoshua Bengio that is sort of getting closer, and they have another work called Object Files and Schemata. So they're really getting very inspired from the 70s psychology and cognitive science on that.
Yeah.
I do think, as far as I understand, and it would be, sorry about the sirens. This is Brooklyn on a Friday night, sirens. So so I was wondering whether you think, how far you think our neuroscience neural networks are from learning those, and whether we could get inspired by at least how those middle layers are learned, not to use transformers for everything, but to just see what are the mechanisms by which we could.
Yeah, and I do think this is exactly like where, potentially that kind of AI type abstract model is pointing in a direction where, okay, we need to understand how these things are actually solving this problem, because they're doing it in a ground up, learning way. It's not building in these structures, it's learning these structures, it's learning how to do these operations. That is what we think hopefully is happening in the brain somewhere. And so maybe if we understood more in detail how that process works, we could sort of take those lessons and apply them to understand how it might work in a more biological system. So yeah, that's exactly the kind of thing that I think would be really interesting. And I don't know if that's what, are you doing that? If so, I would love to hear more about that.
Yeah, so we gotta, hopefully this summer that project will be a little more, because I have a wonderful sort of intern from Princeton who might join if we get the approval. So the whole, it's in the works. And yeah, so that's the kinds of things that
cool.
we're gonna work on the theory side, but also with Anirudh Goyal, we're working on related expansions of the transformers. I think that this is an area that we could learn a lot from doing surgery on those AI models, as opposed to taking them as, taking them as like, wholesale. Yeah.
That's super exciting. So yeah, I'm going to try to learn more about that now.
I will bombard spam your mailbox with these kinds of things as we make progress.
Awesome.
I wonder whether anyone else has any more questions. We are at 6:18. In the past, we have even gone after past 7, but I feel like today it has been so already enriching. I wonder where others are how others are feeling. Do we take more questions or do we wrap up? John, Trevor?
I'm happy. I thought, it was great. This is great. I feel wonderful about the questions, the answers.
Same.
One last question. I had one last question. So Randy, where are you going? What are you going to do next in terms of sort of, you give this whole course where you cover everything, and you have PFC at the end, and Ida raised PFC. Are you planning to do any more in that domain beyond the learning?
So that's a very active area of work. We actually have, there's a couple of papers we're working on right now that are looking at how the thalamic connections with the PFC relate to this kind of predictive learning circuit. And the brief story there is that there's actually 2 pathways into the PFC through the thalamus. One that is basal ganglia gated, okay, and that seems to target more of like the matrix pattern of connectivity, and it's more in the ventral lateral and ventral anterior areas of the thalamus. And then there's this kind of medial dorsal nucleus of the thalamus that is very much like the pulvinar, that has this more kind of what we call core-like patterns of projection into the prefrontal cortex. And so that kind of, those 2 different pathways seem to provide 2 different kinds of kind of like control, modulation, and predictive learning potentially signals in frontal cortex. And so we're really trying to look at that again, kind of, this approach of using the biology to sort of get inspired about what kind of computational principles might emerge from that. But the idea is that somehow that's going to help us understand how these longer timescales of prediction and motor control are being learned in frontal cortex. And then that obviously is critical for having, this sequencing of cognitive operations over time, which is always where our models kind of hit the limit, right? It's like, okay, we can simulate a few cycles of processing of some particular stimulus, but when we need to have coordinated behavior over multiple kind of like seconds or something like that in a neural network model, that's really difficult. And so that level of kind of cognitive sequencing, cognitive control is what's really missing in our models. And we think that these circuits are really going to be important for that. So that's kind of what we're exploring right now.
Fascinating.
John,
thank you very much.
You mentioned? What is the course you mentioned?
Oh, Randy's been teaching a computational cognitive neuroscience course for a very long time, and it was finally, I think, went on YouTube very recently. It's a textbook as well, right?
I didn't know about the YouTube.
You know what?
Yeah, it's a silver lining of the pandemic that I put my course online just to be able to offer it asynchronously, and so I just went ahead and threw the lectures up on YouTube. So now, it's great to have other people be able to access that, and a lot of good comments coming in on that and everything. So it's fun.
Hello and welcome.
A real labor of love, and
Yes. Yeah.
and changing haircuts.
Yes. You can see time passing there for sure. Yeah.
Well,
Yeah.
I really thank you very much for coming. Honestly, you are really game for all these discussions.
Absolutely.
And,
This is
really
fantastic.
awesome.
You know, this is really exciting for me to be able to chat about all this stuff, and feel like I'm learning a lot
Yeah.
as well. So yeah. It's
Yeah,
great
this
what you
is
guys
our
are doing.
pleasure. Yeah, this has been so awesome. I personally learned a lot. I took a lot of notes. I heard that John took notes also, as we saw. We're
Orange notebook. Yes.
I always take notes. And orange.
The old-fashioned way. Yeah.
Orange is the color for my important notebooks.
there you go. There you go.
There we go.
And just Randy, we like to tell the speakers that you can have access to all the questions and all the things that you
Yeah. How does that work?
during
Yeah.
your talk. Yeah. So we have a way. I think Brad and Kanaka and Eva can do that. Right.
Awesome.
Yeah,
Claire,
Claire's
yeah.
going to help you. Exactly.
Yeah.
Cool.
Yeah.
So with that, we should
Fantastic.
also thank them. So thank you, Brad, Eva, and Claire for being behind the scenes. And thank you, Worldwide Neuro. And thank you, Kanaka, although since March she's going to be busy, so she will no longer be always here. But we really are going to miss her every time that she's not around. Yeah, thank you again, Randy. And yeah, I hope everybody
Take
joins.
care.
All right.
Thanks, everybody.
Bye.
Bye.
Bye.